Hi, this is Ms. Park. Today we're going to cover the last topic of our transformations unit. And that topic is the inverse of a function. So let's walk through this little worksheet here that's in your booklet and see what is the inverse of a function. So it's asking us this. It says on the axes provided, sketch and join in the order given the following function. And it's giving us a bunch of points here in this set. So let's plot the points and see what it looks like. So we got -6, -4, -6, -4, -4, 1, and it's saying that to sketch and join. So as we're finding the points, we're just going to connect the dots. Go ahead and do this. -4, 1, -2, 4, 1, 3, sorry for that. Okay, 3, 9, and 5, 7. Okay, and so that gives us this, and it's a function, so I can use function notation on this one. I'll call it f of x. Okay, so now it says, create a function in which each ordered pair from the function f of x has the x and y coordinates written in the reverse order. So for example, the point -4, 1, let's write it as the point 1, -4. So we're going to take each of these points and just swap the x's and the y's. So -4, -6, 1, -4, 4, -2, 3, 1, 9, 3, and 7, 5. So let's sketch those. I am going to actually change pens and do it in a different color. So -4, -6 is over here. It's over here. And 1, -4 is over here. So as you get the points, let's connect them. And then 4, -2, connect. 3, 1, connect. 9, 3, and 7, 5. Okay, and let's look and see what we have. Look at that. Cool, huh? All right, so what do we have? We have something that looks like the original. Now it's funny because it's saying create a function, but if you look carefully, my pink one is not a function because it will fail the vertical line test, right? It fails the vertical line test, so it's not a function, but it looks kind of interesting compared to the original. So you might notice that it looks like a reflection of the original, but not a regular reflection like we know from earlier in the unit with using the x-axis or the y-axis as mirrors. It actually looks like it's reflected in some kind of diagonal line. So it turns out that if we connect the dots of this diagonal line, we see that that mirror line is actually the line y equals x. Okay, and so let's read down below. It says, when you list a function with the x and y coordinates reversed, you create the inverse of the original function. So if that function is f of x, this function is the inverse of f of x. It's the inverse, okay? The notation for the inverse of a function f of x is f with this little -1 superscript of x. Although -1 looks like an exponent in the expression, it is not. It's merely a notation, and we read f with the little -1 as f inverse. So we'll say f inverse of x. Now, notice how small detail, how I labeled this. I said this is the inverse of f of x. I didn't say that this is f inverse of x, even though it's saying that this is how we write it. The reason I didn't do that is because this is function notation. And my inverse is not a function. So I can't use function notation for it. I'm just going to write it's the inverse. Okay, so let's play with some more points. Okay, so suppose you have this set of points over here. It's telling us write the domain. Okay, so we can write the domain. The domain is just all the x values. So we'll open up a bracket and let's write them all. 2, 4, 6, 2, 4, 6, 8, -2, -5. And actually, to be really nice, we will rewrite them in order from smallest to largest. And the range is going to be all the y coordinates. So 3, 1, 5, 2, 5, -1. I'm going to rewrite it. Notice my 5 is repeated. So I'm not going to, there's no need to write it twice. It's already in the set. So I'll just get rid of that extra 5. I'll write them in order. Okay, then it says write the ordered pairs of F inverse. So the ordered pairs of the inverse is going to be the same ordered pairs, but with the x's and y's reversed. So instead of 2, 3, I have 3, 2. Instead of 4, 1, I have 1, 4, 5, 6, 2, 8, 5, -2, -1, -5. Okay. Now it says write the domain of F inverse and the range of F inverse. So the domain is going to be all of the x coordinates. So that's 3, 1, 5, 2, 5, -1, which if I put in order and get rid of the extra 5, I get -1, 1, 2, 3, 5. And the range is going to be all the y values. So hopefully you're seeing some kind of pattern here. -2, -5. I'll put that in order. -5, -2, 2, 4, 6, 8. So what do you notice about the domain and the range? Right, these ones and these ones. Well, if we're going to swap the values of x and y, then we're actually going to swap the domain and the range, right? Because domain's all the x's and range is all the y's. So what is true about the domain and range of the function compared to the domain and range of the inverse? Right, so let's write it in a sentence. So the domain of a function is equal to the range. The domain of a function is equal to the range of its inverse. And the range of a function is equal to the domain of its inverse. Okay, so range and domain, they swap. All right, so that's all the inverse is. It's swapping, so taking any point x, y, and creating the point y, x, swapping the x and y. So what if it didn't have a graph or didn't have a bunch of points, but you had an equation? Right, so that's going to be to the next page. So same idea of swapping the x and y, we're going to do algebraically to find the equation of the inverse. Okay, so let's go to the next page. So let's say, for example, we want to find the inverse of this. We know that this is a line. It's in the form y equals mx plus b. So how do we do this algebraically? We don't have points. So the steps are written out for you. So first thing is, we'll write this out in xy notation. All right, just change f of x and write it as a y. Then this is the part where we're going to swap the x and y. So for f, it looks like this. But if we want to get f inverse, we swap the x and y so that it looks like this. Okay, and then to write it like an equation that we're kind of more used to seeing, we like to write our equations with the y isolated. So I'm just going to isolate that y, divide both sides by 4, and I get this equation. So I get, I'm just going to rewrite it over here, y equals x minus 3 over 4. All right, and actually, if you don't recognize what this is also a line. So, because we can split this into two parts. So this is y equals 1 over 4x minus 3 over 4. So it really is y equals mx plus b. And because this is a function, because if I sketch this, it will pass the vertical line test, I can actually replace the y with f inverse. So f inverse of x is 1/4 x minus 3/4. All right, and that's the equation of the inverse, completely algebraically. Let's do another one. Let's find the inverse of this radical function. All right, and it's asking, is the inverse a function? So let's see. I'm going to let's first sketch it and see what it looks like. Okay, so this is a radical function that has been transformed. It's been translated 2 units to the right. So this is the radical function, looks like this. And this is 2. Okay, so now let's see what the inverse equation, the equation of the inverse is going to look like. So step 1, we'll work with just g, but we'll call it y equals. Okay, so we're going to switch to xy notation. Step 2, we're going to swap the x and y. Okay. Step 3, we're going to isolate the y. So how do I undo this square root? I need to square both sides. So I'm going to get x squared equals y minus 2, and then get y alone. So y equals x squared plus 2. Okay, so let me sketch the inverse. So what is y equals x squared plus 2? And actually, I'm going to write it like this. Y equals x squared plus 2. Is that a function? All right, yes, it is. That's a quadratic that's been translated up 2 units. So I can actually write f inverse. Sorry, I'm going to write the inverse in there. Because it's a function, I can use function notation. So say f inverse of x equals x squared plus 2. All right, so now let me sketch that. So x squared plus 2 looks like this. Now it would make sense that if there's a point at 2, 0, then the inverse would have a point at 0, 2. So it would make sense that the inverse has a point right there. All right, and x squared plus 2 should look like this. All right, so if this is g of x, then I can write g inverse of x for that one. But you should kind of question this, because didn't we say that the inverse is a mirror image in that diagonal line y equals x? So this doesn't look like a mirror image, right? How come that one has just like one of the parts and this one's got the 2 parts, right? And the reason that happened is because when I squared both sides, I actually introduced an extra solution that's not really there. It's called extraneous solution. Because by squaring both sides, I would get the same answer if that was a positive root y minus 2 or a negative root y minus 2. So it's as if I would have that radical have that positive one and also the reflected one, right, when I'm squaring it. But my original was only the positive radical, only like the regular one that was translated over by 2 units. So this entire thing is not my inverse, is just this part, right? Just this pink part, that's my inverse. The rest of it is not really there. So when I'm writing what my inverse is for this one, I have to say it's not all of it. It's not all of x squared plus 2, but it's only the part where the x's are greater than or equal to 0. It's only this part on the right. So this other part's not really there. I'll make it a dashed line on the other part. I'll make this dashed so that you see it's not really there. It's not really part of the inverse. Only this pink one is the inverse. So I'll make this one solid. Okay, so we have to say that the inverse is not the entire thing that we got algebraically. We have to think about what does that look like. If my original looked like this, then there's no way my inverse could be the entire parabola. It's just going to be part. Okay, now you'll notice something else that's interesting. The word inverse means the opposite. So what's the opposite of taking the square root? Is squaring. So what's the opposite of radical? Is squared, right? So that's they kind of go together. So in the next example, I have a quadratic and it's asking for the inverse. So think about what's it going to look like. If the quadratic is something squared, what's the opposite of squaring, right? Square root. So we're expecting that the inverse should look like a radical function. So let's see. So it's asking us to sketch this and its inverse. And also, let's find the equation of the inverse. But we'll start with the sketch. Okay, so this one is a quadratic. It's got vertex at 3, 1. So 3, 1. So I'm just going to put a 3 here and a 1 here. And I can see that it opens upward. Okay, and this is my f of x. Okay, now let's see what the inverse is going to look like. So instead of 3, 1, I'm going to have a point 1, 3. Right, so I'm going to have a point 1, 3, kind of right there. All right, so that's going to be for the inverse. And I know it's going to be some kind of reflection of this, but in which direction? So here we remember that the domain and range swap with the inverse. So if the range of this one here is going to be everything greater than or equal to 1, then that means the domain of this one here is everything greater than or equal to 1, right? The domain and range will swap. So this is my inverse. That's my inverse. All right? So this is the point. So let's write that again. So this is the 0.13, but this is the 0.31. Okay, and so they swap. You'll notice that the domain of the original is all real numbers, and the range of the inverse is all real numbers. Okay, so let's work on this algebraically and figure out the equation of this inverse. All right, so first step is I'm going to work on just f, but I'm going to replace the f of x with y. Second step, for the inverse part, I'm going to swap the x's and y's. Then I'm going to try to isolate y. Now I could think about expanding all this and isolating y, but we ran into trouble with stuff like that before. Because if you expand this, you get y squared term and you get y term, right? Expand this properly, y minus 3 times y minus 3. And you have an x, and it becomes very difficult to isolate the y. So we leave it the way it is and just rearrange the equation to take stuff away from y until you're left with just y. So the first thing we take away is this plus 1, because that's kind of the last thing that was added. So I have x minus 1 equals 2 times y minus 3 squared. And now I'm still trying to undress that y, take things away from it. So I'll divide by 2 both sides. X minus 1 over 2 is y minus 3 squared. Now how do I get rid of this squared? I do the opposite. So I'm going to take the square root of both sides. But remember that when you take the square root, it introduces a plus or minus. Okay, and now here I can bring the minus 3 over and it becomes plus 3. And that is my equation. And the question is that a function? And we should say no, of course not. First of all, there's a plus or minus, and that tells us that there's 2 values for y for every value of x. So that's not a function for sure. But look at the picture. Right? With the picture, we can see that fails a vertical line test. So it's not a function. So I am not going to use function notation. I'm just going to write y. So let me just write it this way. Okay, now it says restrict the domain of f so that the inverse is a function. So right now, this is not a function. But the question is saying is, you know, the problem is, the reason we didn't get a function is because f had these 2 parts. That when you take the inverse, your inverse has these 2 parts, and that makes it not a function. So how could we have taken only a portion of f so that the inverse of just that portion would have been a function? So that's what it means by when it says restrict the domain. How about we take just part of the domain of f so that by taking just that part, the inverse of just that part is a function. So what could I take? So let me just write here, restrict the domain of f so that the inverse will be a function. what should I take? Well, if I take both parts of f, for sure I don't have a function for the inverse, but if I take one of the parts of f, I will get take the other part. So I could take the part that says x is greater than or equal to 3, that would be the right side. Or I could take the part where x is less than or equal to 3, that would be the left side. And if I take just one of those parts and not the whole thing, then the inverse of those parts will be, of each of those will be a function. And the last thing I want you to notice is, remember I said in the beginning, what's the opposite operation of squaring? Is square root. So notice that the inverse has a square root in it. And if you look very carefully, this is just a radical function, right? It's 1/2 x minus 1. So it's got transformations in it, but that's just radical. And the reason there's two of them is because there's the positive radical and the negative radical, right? And that's how they're related. Okay, I'm going to stop this page here. You've got practice in your booklet with a number of different graphs. So just practice with interchanging the x and the y's, and then also practice with writing the equations. Okay, thank you for watching.